Assalamu alaikum. My name is Hachem. Today I will be presenting our work static detection of IoT malware using grayscale image representation and lightweight convolutional neural network. This work is collaboration with my supervisors Mejdi, Kaddour and Hachem Guerid. I'm so happy to be part of the International Conference CommNet 2022. The IoT devices are increasingly used every day because they convert everything linked and smoothly integrated. They enable the deployment of broad scope of creative and helpful services in various fields. We can find it everywhere, such as smart manufacturing devices, healthcare, agriculture, transportation, and industry. There will be approximately more than 70 billion connected devices by 2013. But the widespread of IoT devices has made it a good target for adversary to carry out a very sophisticated cyber attack. In 2016 happened one of the largest and most disruptive DDoS attack. We saw critical infrastructure go offline, the ISP service, internet service provider lose their services, and degradation in cloud workload. We saw the first IoT malware back in 2008 with Hydra, but that didn't seem to prepare us for Mejdi 8 years later. The Mejdi attack was a big event that demonstrated the impact of vulnerable IoT devices on the internet. We are seeing new targeting of firewall devices, home routers, TVs, DVRs, and other devices. So, are we as a security community prepared for the next Mejdi-like attack? Unlike the Windows malware, which targets mainly architecture Intel and AMD, IoT malware compiled in various different architectures such as ARM, Spark, PPC, Intel, and so on, to infect a huge range of different machines like smart home devices, cameras, phones, and healthcare devices. But the challenge here is that the IoT malware based on Linux operating system, where the most of antivirus vendors and the most past research were focusing on securing the Windows operating system. The actual challenge here is for the malware detection in Linux is the low visibility, and the low visibility imply on low detection rate. To analyze this malware, there is two main approaches, static approach and the dynamic approach. The dynamic approach used by compiling the malware analyze its behavior. However, this method is time and resource consuming. Static approach, we don't need to execute the malware. It's based on extracting the information from the different section of the malware. Otherwise, the static method commonly search for well-identified string signature inside the binary. But definitely the attackers are so smart they may completely remove or modify the section of the binary file to confuse the malware analyst and make it harder to understand the work of the malware using some technique like obfuscation. Now, artificial intelligence and machine learning work on both sides, cybersecurity professionals and hackers. At this moment, deep learning comes into force and sets new roles in the game. Deep learning based method outperform classical method in all tasks that are too complex to describe using rules. We put an hypothesis that malware are built mostly using the same code source, or sharing the same code source, which may give us the ability to detect the similarity of the code in the malware. To check this hypothesis, we convert the malware binary into grayscale image. The main idea is to transpose the CNN methods used for image classification, which have demonstrated their effectiveness, into malware classification by converting the binary malware into images, then classify them based on that. We applied a new generation of static malware analysis using convolutional neural network to classify IoT malware based on their families. We focus in this paper on the static analysis of IoT malware in the ELF format in order to map the embedded malware to well-known family, or otherwise to classify it as a known malware type. And this is a representation of different IoT malware families. As you can see, that image representation of the malware gives more information about the anatomy of the binary. We can see clearly that most of the malware from the same family share the same patterns. Even if the attacker used some technique like obfuscation, the general view of the image will stay the same. The first step in our methodology is converting the binary file into grayscale image or into images. This methodology suggested by Nataraj relies on converting the ELF malware samples into grayscale images. Each byte from the malware binary represents a grayscale pixel ranging from 0 to 255, where 0 is the black and 255 is the white. The criteria of choosing the width is depending on the file size, as we can see here in the table on the right. Images gives more information about the structure of the malware. We can see that various subsections have different texture. The width of the images relies on the size of the image or the file, where the height also varies depending on the file size. I want to refer that we are not the first IoT malware study in this field. There is a lot of paper that looked at specific malware families, looked at IoT malware in general to study their characteristic, and even Linux malware that overlaps with IoT malware. This paper provides a fascinating perspective into this landscape, but they only give us a partial understanding. For example, a lot of datasets are small, ranging from hundreds of samples to thousands of samples, or they identify just a few classes. Taking an example, two recent studies, they use image representation methodology. The first one is deep study. They designed a multidimensional model to classify IoT malware based on image representation. Of course, part of this framework is to classify malware images using combined CNN LSTM method using a set of 10,000 malware sample, where they classify only 4 families. The second study, they also focus on image representation, classify the malware based on image representation, where they classify the malware into 2 classes, benign or malware. Well, also they use only 500. Note that unlike our work, most of studies filter out the obfuscated binary, since their strategy is mainly based on readable ASCII strings found in the malware samples, which reduce the detection rate of the malware if it was obfuscated. There is many challenges to study IoT malware. First, there are no large-scale data set for researchers to study IoT malware, and most of the data is collected through short-lived honeypot. And as prior work has shown, IoT malware can detect and evade honeypots. Secondly, there is limited tools to analyze a Linux malware, because the IoT malware targets multiple architectures like ARM, MIPS, Spark, and so on, and many more of that, which take us to build specialized tooling to handle these differences. We were able to collect more than 89,000 malware samples over the past 3 years, from 2019 to 2022, from main public malware repositories such as VirusShare and Malshare. Taking in consideration the families that has most number of samples, we were able to predict correctly 9 malware classes by classifying more than 11,000 malware sample by taking the first predominant families such as Mirai, Gavji, Tsunami, and the others. The Mirai malware was the predominant family with more than 52% of dataset. Moreover, we didn't filter out obfuscated binaries. We found about 50% of the samples of our dataset using obfuscation techniques, where 97 of PNScan malware family, we're relying on obfuscation technique, unlike GovJet and Exodus. We label the instance with AV class tool, which drives the most likely name of the instance based on the combination of analysis reports from different antivirus vendors. Now we will give a brief details about our model. This model consists of 4 blocks. The first 3 blocks are formed by 2 convolutional layers with different filter size, followed by a max pooling. The convolutional operation is focusing on extracting the feature from the input, where the max pooling layer is reduce the size of the input by preserving the important features. The feature map obtained from the max pooling layer is converted into one-dimensional array. In the 4th block, we have 3 fully connected layers with different filter size and softmax activation function in the output layer of the for the multi-class classification, and by adding different filter sizes of dropout to control the overfitting. This this table is a representation of different hyperparameters used in this experiment. We trained our model using different image sizes, 64, 128, and 224. We divided the data set based on 80% for training and 20% for testing. We used the technique of cross-validation to handle the problem of imbalanced data sets. We applied the ELU activation function as it leads to lower training times and higher accuracies compared to a ReLU. We applied all our experiments using platform as a service which provide us with a good machine that has a high computing power. And this chart is global representation result. As we said that we trained our model using different image sizes. As it was expected, the more is the image size, the best result we get. We get 95% of accuracy and 89% of F1 score using our model to classify 9 families, which is higher compared to other models. We can confirm that even the families that has smaller number of datasets can be predicted with high accuracy using our model to Hachem CNN model. We got 81% of accuracy from the PNScan family, where there 97% of the sample, the PNScan malware samples, are obfuscated, which demonstrate the performance of our methodology. Naturally, the more is the size of the image, the more time required for training. Computer time increases only by 35% in our model, from 64 by 64 image size to 224 by 224 image size, and less time needed compared to other models. To conclude the presentation, we suggested in this paper a static IoT malware classification approach based on new lightweight CNN model applied on grayscale images. We didn't filter out the obfuscation malware and thought we got 95% of accuracy compared to other tested model. It's necessary to take into consideration that a considerable number of samples didn't detected or labeled by the existing antivirus vendors, which shows the limitation of existing malware detection product. As future work, we plan to design a multidimensional approach to consider also structural knowledge and qualitative features of ELF binaries such as string or header fields. Also, we may experiment sequence learning models to represent malware as a sequence of code portions instead of a single grayscale image. And by that, we reach the end of the presentation. And you can contact us using LinkedIn or the email if you have any questions or you want to know more details about the paper.